Okay, so I recorded a whole video and then realized it was only capturing the upper left of the screen. So here we go again. I'm gonna go a little faster this time because I've already done all the writing up, and so, oh well. So for this last theorem we have let n be a natural number and let a be an integer. If a equals n cubed plus r, and r is between 0 and n, including 0, not including n, for some integers q and r, then a is equivalent to r mod n. And so the corollary is that if n is a natural number, then each integer is congruent modulo n to precisely one of the integers, 0, 1, 2, all the way to n minus 1. That is, for each integer a, there exists a unique integer r such that a is equivalent to r mod n, and 0 is between, and r is between 0 and n. And this is the kind of our theorem that really connects like the computer science idea of modulo n to the math idea of modulo n. Okay, so first we have this example. The example proposition is that for each integer a, if a is not equivalent to 0 mod 5, then a squared is equivalent to 1 mod 5, or a squared is equivalent to 4 mod 5. And so we're going to prove this using cases. And so that corollary says basically if n is 5, then modulo n numbers can be modulo equivalent to 0, 1, 2, 3, or 4. So that gives 5 cases, but then we're not including 0, so there's 4 cases. So case 1 is when a is equivalent to 1 mod 5. Case 2 is when a is equivalent to 2 mod 5. Case 3 and 4, so on and so forth. So the proofs are provided in your book for 1 and 4, and I'll follow those proofs real quick. So when a is equivalent to 1 mod 5, then in this case, theorem 3.34 says a squared is equivalent to 1 squared, or you can simplify then because 1 squared is 1. So that proves that a is equivalent to 1 mod 5, and if a is equivalent to 1 mod 5, then a squared is equivalent to 1 mod 5. The fourth case is when a is equivalent to 4 mod 5, and in this case, use theorem 3.34 to conclude that a squared is congruent to 4 squared mod 5. 4 squared is 16, so another way to say it is a squared is equivalent to 16 mod 5. We also know that 16 is equivalent to 1 mod 5. So the transitive property, using theorem 3.6, tells us that a squared is equivalent to 1 mod 5. So then we summarize the case. If a is equivalent to 4 mod 5, then a squared is equivalent to 1 mod 5. Now, by the way, for LaTeX, to do like the mod something, you can do mod 5, or so p mod is like mod with parentheses around it. P mod, like if you got more than one digit, like say 15, you would do that for like mod 15. But if you've only got one digit, like 5, you can just do space 5. Okay, so case 2 is when a is equivalent to 2 mod 5. Theorem 3.4 gives us a squared is equivalent to 2 squared mod 5. So a is equivalent to 4 mod 5. Thus, if a is equivalent to 2 mod 5, then a squared is equivalent to 4 mod 5. That was a fairly simple one. When a is 3, we have the extra step because then theorem 3.4 gives us that a squared is equivalent to 9 mod 5. And we know that 9 is equivalent to 4 mod 5. Therefore, like using theorem 3.6, that equivalency is transitive, we know that a squared is equivalent to 4 mod 5. And then I would write up a final sentence saying, having proven all 4 cases, we now see that if a is not equivalent to 0 mod 5, then then a squared is equivalent to 1 or 4 mod 5. Okay, so that completes the last part of this section.